Hello, everybody. So this is an optional section or extra section of section 5.5, which is on triple integrals using cylindrical and spherical coordinate systems. Now, for cylindrical, it's not that bad, okay? But for spherical, dv ends up being this pretty long expression. And in the main part of the video for section 5.5, I just assume that you know what dv is, okay? And we'll use that. But this short video is to explain why dv has to be that long expression. All right, so here we go. What is dv in spherical coordinate systems? All right, so here is a short video on as a part of section 5.5, but what is dv in spherical coordinates? All right, so as you know, in rectangular coordinate system, dv is easy. It's dx, dy, dz, or any of the 6 permutations of it. For cylindrical coordinate system, that's also pretty easy. dv is r times dz, dr, d theta. All right, not a problem. For dv in spherical coordinate system, there is a problem, okay? So let's find out what the dv is as you enter into these spherical coordinates and try to figure out triple integrals. All right, so here's a picture of what we will be doing. Okay, so you have the sphere, and you know that in spherical coordinates, we denote with rho. This looks like P in our alphabet, but this is the Greek alphabet letter rho, which describes for you what that radius is, right? And then we are trying to pick, of course, a little tiny piece. We call this like a little block, a chip on the block, right? So this little block is what you see. It's just a part of this, okay? I don't know if I want to circle this part, but you have this big sphere, right? And what is the circumference of the sphere? Okay. Well, clearly it's just 2 pi times the radius, rho, right? So if you go the entire thing, like if this whole equator is going to have that circumference, which is 2 pi times rho, all right? And then we take a small piece of the surface of this globe, and that's what I include, or I color it as orange. Okay, so this is the orange part. What you see here is exactly that little piece there. And then we also cut the tiny piece, just peel it off the surface, all right? And so it has a little thickness, and the thickness here is what I refer to as delta rho. Okay, so you have this outside rho, and then if you just peel, if you take a little slice of it, you know, like if you think of this as the Earth, okay, you're digging a little hole of depth delta theta, delta rho, okay, delta rho here, and that's the thickness of this little block. Of course, the objective that we have right now is to find approximate the volume of this block, and we are going to let delta rho, delta theta, and delta phi get smaller and smaller, infinitesimally small, so that you can have based on this delta v, you can find what dv is. All right. So let's try to focus on finding the volume of this little block. Okay, that is what we will be doing. Okay, so think of this as a sort of it's not exactly a rectangular box, but if you think of this tiny block, you can think of this as, or similar to a rectangular block. It's got this thickness, delta rho, right? It also has this width, right? And how wide is this little square area? And how tall is this rectangular area? I have color coded this. So what you see here in bright green, okay, is the height, which I will denote as h, all right? And you can also see that it's over here, right? It's really not that hard to find out what that thing is. And then with yellow, I have highlighted the width, w. Okay, so that's what this is. And you can also see that over here on the left in this picture here. All right, so what is dv? All right, well, delta v, of course, is delta rho, that's the thickness, times h, the height, times w. Okay, that is because it is pretty much approximated by a rectangular box. All right, so with that in mind, let's try to figure out what h is, the height, the green part. Okay, what is this height? Well, I think you can tell, right? If you look at this line, so this block here, if you look at this line here, this is a part of the circumference, right? So, how much of the circumference are we talking about? It is basically, and think about this, maybe this is the better way to think about this. We're trying to find this length here, okay? And how much of the circumference are we taking as h? Okay, well, it's pretty simple because h is delta phi. Now, if delta phi happens to be like 1 degree, then we're talking about 1 out of 360th of the circumference, right? If this happens to be 2 degrees, then that's 2 degrees divided by 360th, and then you multiply that by the circumference. So it's delta phi divided by 2 pi. Of course, that is equivalent to 360 degrees. So it's this much of the circumference. I think that's pretty easy. What is the circumference again? Well, we know that the circumference is 2 pi rho. Okay, so all you really have to do to find h, let me just erase this, is so therefore h is equal to delta phi divided by 2 pi times the circumference of 2 pi r. Well, of course, the 2 pi's will cancel. So the answer is delta phi times rho. Okay, so it's rho times delta phi. Don't say it's all Greek to me, because yes, it is all Greek to you, right? Except H. H is English, right? Everything else is Greek here. All right, so H is rho times delta phi. Not a problem, right? All right, so how about W? That's the last thing we need to find this. Now, W is a little tricky because W, all right, if you just watch this here, the yellow line here is right here. And so we need to figure out this little small thing here. Okay, how wide is that? How wide is this little block? Well, it is just like what we had before. Okay, so the difference between the two angles in terms of theta is, of course, delta theta. Okay, that's how we write, the difference, right? So delta theta out of 300, if delta theta is 1 degree, again, we will be considering 1 out of 1 divided by 360 of what? Okay, that's the hard part of this purple circumference. Okay, but that's not 2 pi rho anymore. This actually depends on where this purple line is. I mean, this looks like a latitude line, right? And because this circle, the purple circle, gets smaller and smaller as you approach the North Pole. And it is the biggest at the equator, right? And so that depends on what phi is. And in fact, in this picture, you can see, you see where the phi is? This is phi. And the purple line, or the purple latitude line, which I drew here, depends on this phi, all right? So it is, okay, let's go ahead and write down what W is. W is delta, oh, I should use black here, delta theta out of 2 pi, right? If delta theta is 2 degrees, we are talking about 2 divided by 360 of the here, now we're going to use purple, right? Of the circumference of the purple circle. And so, I mean, what I mean by this purple circle is the latitude line or latitude circle described or colored in purple. All right, so what is this circumference of the purple circle? Well, we need to find this radius, okay, but this radius is pretty clear, right? Well, that radius happens to be, well, look at this. You have, this is rho. Oops, I probably should not use that same color. All right, so that you have this rho, and you have phi. And what is the radius here? Well, that turns out to be the opposite side relative to the angle phi, right? So this will be rho times sine phi. Did you get that? The length here is rho times sine phi, just by simple trigonometry. All right, so so the purple circle has the radius of rho times sine phi. That's the radius. All right, so the circumference of the purple circle is going to be 2 pi times the radius, right? And the radius is rho sine phi. So this is the circumference, the description or an algebraic expression that describes the circumference of the purple circle. And so now W is delta theta over 2 pi times 2 pi rho sine phi. Of course, the 2 pi's will go away. And so this turns out to be rho sine phi times delta theta. Okay, we have all the ingredients we need. We have H, we have W, and we have delta theta, right? So here is, the delta rho is what I meant, right? And so here's the final thing. When you put this together, okay, delta V, right? Remember what delta V was? It's delta rho times the height times the width. But now we know that the height, remember what height was? Rho times delta of, phi, rho times delta phi. Okay, and then W turns out to be rho times sine phi delta theta. All right, so what we have here is, how many rows do we have? 1, 2, and then you have delta rho here, but that doesn't count. All right, so this is rho square, right? And then you have sine phi, okay? And so that part is taken care of. And then the rest is all deltas, right? So you have delta rho, delta phi, and delta theta. All right, so this is the description of delta V. Delta V happens to be rho square, sine phi, delta rho, delta phi, delta theta. All right, and as we, let all of these become, so delta rho becomes d rho, when you make them infinitesimally small, delta phi becomes d phi, and delta theta becomes d theta. And as you do that, of course, delta v becomes dv. All right, so here's the conclusion of this whole matter. dv is equal to rho square sine phi d rho d phi d theta, and say it about 3 times and then start having a little tempo or rhythm. So it's dv is equal to rho square sine phi d rho dv d phi d theta. What did I say? dv is rho squared sine phi d rho d phi d theta. Rho square sine phi d rho d phi d theta. Rho square sine phi d rho d phi d theta. All right, so that's what dv is. It's rho squared sine phi d rho d v, sorry, rho square sine phi d rho d phi d theta. All right, use that anytime you use, try to integrate find a triple integral in spherical coordinates to replace that dv with rho squared sine phi d rho d phi d theta. Okay, that's it for this lesson.